Imagine a cosmic mystery so profound that it could rewrite our understanding of the early universe. The James Webb Space Telescope, JWST, has just thrown a wrench into the story of Earendel, previously hailed as the most distant star ever discovered. What if, instead of being a single massive star, Earendel is actually a cluster of stars? This is the intriguing question posed by a new study published in the Astrophysical Journal. https://iopscience.iop.org/article 10.3847-2041-AD93 meta, which challenges everything we thought we knew about this ancient celestial object. When Earendel was first spotted by the Hubble Space Telescope in 2022, it was a groundbreaking discovery. Located a staggering 12.9 billion light-years away, Earendel appeared to be a solitary, massive star that had formed just 900 million years after the Big Bang. This placed it in the era when the universe was still in its infancy, making it a crucial piece of the puzzle in understanding the early cosmos. However, the latest observations from the JWST suggest a different story. Using the advanced capabilities of the JWST, particularly its near-infrared spectrograph, NIR-SPEC, researchers have delved deeper into the light emitted by Earendel. What they found was surprising. The spectral features of Earendel closely resemble those of globular clusters, dense groups of stars that are typically found in the present-day universe. This means that Earendel might not be a single star at all, but rather a compact cluster of stars that formed from the same gas and dust cloud. What's reassuring about this work is that if Earendel really is a star cluster, it isn't unexpected, explained Massimo Pasquale, an astronomy doctoral student at the University of California, Berkeley, and lead author of the study. Our findings suggest that Earendel is consistent with how we expect globular clusters to have looked in the first billion years of the universe. To understand why this discovery is significant, it's important to know how Earendel was first detected. Gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, played a crucial role. This cosmic effect occurs when a massive object, such as a galaxy cluster, bends and magnifies the light from objects behind it, acting like a giant magnifying glass. In Earendel's case, a massive galaxy cluster between Earth and the distant star amplified its light by a factor of 4,000, making it visible to our telescopes. Without this lensing effect, Earendel would have been too faint to detect. However, the lensing effect also introduced a layer of complexity. The magnification made Earendel appear much larger than it would have in its natural state, leading astronomers to question whether it was a single star or a more complex structure. This led to the hypothesis that Earendel might be a star cluster, an idea that gained traction as the research progressed. The study's findings on Earendel's age and metal content further support the star cluster hypothesis. The light spectrum captured by the JWST's instruments revealed that Earendel's properties closely match those of globular clusters found in the local universe. These clusters are ancient structures composed of hundreds of thousands of stars formed from the same material, characterized by their compactness, old age, and high density. After some recent work showed that Earendel could be much larger than previously thought, I was convinced it was worthwhile to explore the star cluster scenario, Pasquale said. His team's analysis indicated that the object's size and composition are consistent with a star cluster, possibly one that formed in the early universe. Despite the compelling evidence, the study is not without its controversies. Brian Welch, a postdoctoral researcher at the University of Maryland and NASA Goddard Space Flight Center, who played a key role in Earendel's initial discovery, noted that the spectral data from the JWST might not be sufficient to definitively classify Earendel as a star cluster. At the spectral resolution of the NIR-SPEC instrument, the spectrum of a lens star and a star cluster can be very similar, Welch pointed out. It's important to consider all available data when attempting to classify these highly magnified objects. Welch also raised concerns about the scope of the study, suggesting that focusing solely on the star cluster hypothesis might have overlooked other potential explanations. For example, Earendel could be a binary system or even a different type of cosmic object. The measurement is robust and well done, but in only considering the star cluster hypothesis, the study is limited in scope, he added. So what's next for Earendel? The debate over its true identity is far from settled. Both Pascal and Welch agree that monitoring changes in Earendel's brightness could provide crucial insights. Microlensing, a phenomenon where smaller objects temporarily distort the light from distant stars, could help determine whether Earendel is a single star or a cluster. Microlensing effects are more pronounced in smaller objects, which would help distinguish between the two possibilities. It will be exciting to see what future JWST programs could do to further demystify the nature of Earendel, Pascal concluded. As the scientific community continues to investigate this enigmatic object, one thing is clear. The story of Earendel is far from over, and it promises to keep us on the edge of our seats. What do you think? Could Earendel be a star cluster, or is there another explanation? Share your thoughts in the comments below.